Okay, so section 2.3 dealt with the invertible matrix theorem, and we learned that this is theorem 8 from section 2.3. All of these statements are either all true or all false. And I think it would be useful to just try to true, and section 2.4 is not part of, 2.4 is not formally a required section in Math 284. So that's why we are letting that section go. But section 2.3, which is right here, I think it would be good to try to prove one of these results. So, like for instance, one result is, well, if we have if A is invertible, then the columns of A span the n-dimensional space. So if you have an n by n matrix, and the columns, and A is invertible matrix, then the columns of A span n-dimensional space. Okay, that's a sort of an amazing result. I mean, here we're relating invertibility of a matrix to a span, okay, for the columns of a matrix A. Let's try to understand why that's true. Okay, because you're going to have like in your homework for section 2.3, you're going to have you know, some of the questions are going to reinforce this theorem. So let me see here. Let me just bring it up. One moment here. Okay, take a moment to copy this example down, and then we'll work out the proof. All right, so let's take a look at this. Well, you know, we're told that we have a square matrix. Okay, well, we have a square matrix. Anytime we're talking about invertible matrices, we have to be talking about n by n square matrices. And we want to show that if A is invertible, then the columns of A span R sub n. Now, so what you're doing is you're taking, and let me just move this down a little bit here. You're taking this piece of information, A is invertible, so think of that as like P, and you're trying to prove another statement that the columns of A span R sub n, Q. So what you're doing here is you're trying to prove that statement P implies statement Q. Now, based on the invertible matrix theorem, actually, the statements are equivalent. So not only does P imply Q, but Q implies P. But for now, we're gonna go this direction. Okay, so let's go ahead and look at the proof here. Okay, so what I did was I have the matrix A, and I'm expressing the matrix A I'm writing it in this form where I'm expressing the matrix A as its column vectors. I'm writing the matrix A in terms of its column vectors. Every column vector has size n by 1. And okay, if that matrix A is invertible, then for every vector B in n-dimensional space, the system of equations, AX equals B, has a solution, X equals A inverse times B. Okay, that's absolutely true. Now, what our goal is, of course, is to relate the span of the column vectors of A. I mean, well, that's where we're going. Okay, but for now, this is true, and why, if A is invertible, would the system of equations AX equals B, why would that have the solution X equals A inverse times B? Well, I show it below here. It's not hard to show. Okay. I mean, there I show it. I multiply the matrix equation by A inverse both sides. I can do that because since A is invertible, the inverse of A exists. And A inverse times A is simply the identity. And the identity then times the vector X is just X. The key now to relating, the key to proving our result that the columns of the matrix A span n-dimensional space is this matrix equation. This matrix equation can be written, A times X equals B. That matrix equation can be written as what other type of equation? So this is a matrix equation. But matrix equation can be written as a vector equation. That's right, Mikhail. And that's what we're going to do. We have a matrix equation that has a solution vector X, and we're going to write it as a vector equation. Okay, so if I go to the next page to show you this, what would the vector equation look like? Well, for the matrix equation AX equals B, this is the corresponding vector equation. It's a linear combination of the column vectors of the matrix A and you set that equal to the vector B. So in other words, A times the vector X equals B is equivalent to this vector equation. It's equivalent. And we know since the matrix equation, since A is invertible, the matrix equation A times X equals B has a solution vector X. Well, equivalently, the vector equation has a solution vector X for every vector B in n-dimensional space. Therefore, if you were to pick any vector B in n-dimensional space, there's going to exist a linear combination of the column vectors of the matrix A whose that will equal the vector B. The vector B would equal some linear combination of the column vectors of the matrix A, because to find the linear combination, you need to find the weights, x1, x2, x3, all the way up to xn. But we know those weights exist because A times the vector x equals B is guaranteed to have a solution because A is invertible. And therefore, for any vector B in Rn, B would have to be in the span of the column vectors of the matrix A. And so the columns of A span n-dimensional space. Okay, let me make sure everybody's comfortable. Let me know if you have any questions on that. Linear algebra is really, they say it's the first course where students are actually exposed to the method of proofs, like you're seeing here. I mean, I'm not sure that's exactly true, but certainly the proofs you're seeing, they're very different than what you would see like maybe in a calculus course. Um, well, somewhat different. Let's put it that way. And you'll. Did you see that in 207, Mikhail? Well, sure. Yep, in 207, they'll have that. So, you know, it's a great course because you get exposed to proving things. And the exercises in the book, particularly the multiple choice exercises in the homework, emphasize a lot of conceptual ideas. Let me see. Hold on. There was a chat message here. Okay, definitely. Excellent. Excellent. Now, let me just do one thing here. Hold on here. One moment, class. Just give me one moment. One moment. You have to forgive me. What I'm doing is I'm in MATLAB. I'm trying to, okay. All right, one moment. I want to show you, yeah, okay, good. So this is fine. All right, let me bring up MATLAB for a moment. So are there any questions before I move on here? Okay. So in one of your homework questions, I believe it's in section 2.3, they talk about something called a condition number, okay, for a matrix. And I want to mention what a condition, just discuss it with you. So what's like the friendliest, most, like an invertible matrix, that's like the nicest invertible matrix you can think of? The identity. That's right, Mikhail, the identity. Okay. So if we type in the identity here, there it is. Let's just do a 2 by 2. If you compute what's called a condition number on that matrix, hold on here. Now wait, there was a chat comment. Yeah, if you compute the condition number on the identity matrix, you get a 1. Okay, so 1 is very, very nice. Okay. Now, what I want to do, let's think of another matrix here that is close to being non-invertible. Okay, close to being non-invertible. So if you look at the if we look at the invertible matrix theorem here, back in the textbook, it says that the matrix A, if the matrix A is invertible, if we were to focus here, let me take this off. Matrix A is invertible. Okay, well that means that, like for instance, if the matrix A is invertible, then the columns of the matrix A form a linearly independent set. Okay, so like for instance, now if we go back to MATLAB, hold on here, let me get it back. If we go to MATLAB, this identity matrix, which has columns 1, 0, 0, 1, I mean, we know that 1, 0, 0, 1 are linearly independent vectors. You know, think of I and J on the XY plane. You can't have any more linearly independent than that, so to speak. You know, they're at right angles, right? Those vectors have a right angle between them. But so if a matrix A is invertible, its columns are linearly independent. So what I want to do is I want to here now have a matrix A where, let me see, let me just write something down here. I'm going to write a matrix A. I'm going to write this down. I'll show you. 1, 2, and 1 and 1.99. Okay, and let me do a CLC and bring it up again here. So what do you think about this matrix A? Hold on, I don't like what I have here. Hold on, no. Let me do it again. That's not what I want. CLC will clear. Okay. Actually, I can bring up the script editor here. Okay, and that's a feature in MATLAB. And the first row I want 1, 1, and the second row I'm going to have 2, 1.99. Okay. And if you notice here in the script editor, this is a nice place to write in your code, because look at the top right. If I take that bracket off on the top right, what do you see up there? What color do you see on the top right of the editor? What color is that warning? Red. Red means it won't run. That's like a stoplight. You know, you can't go with a red signal. And you see, Matt, and if we click on the little thing here, it gives you sometimes clues as to what might be the problem. Well, the problem is we don't have an end bracket. Now, if I put the end bracket in, I've gone from red to yellow, and they're just giving sort of a little warning there that I can suppress output with a semicolon. But this should run. So what I do is I copy it. I copy the code from the editor. And remember, stuff you do in the editor, you can save to a flash drive. Right? Copy it, paste it, and then hit enter. And there's my matrix A. what do you think about the columns of this matrix A? Are they linearly independent or linearly dependent, the columns of the matrix A? So the first column is 1, 2. Second column is 1, 1.99. Technically, those are linearly independent. That's right, Mikhail. But the second vector is almost the same as the first vector, right? Almost the same. Right, so they're similar. So watch what I do when I put a condition number on the matrix A. You see that? We got 996. We got a big number. Okay, and if I go back and adjust the matrix A, if I use something called format long, and then bring the matrix A, well, actually, hold on, I'm going to use format long. Okay, and here's my new matrix A, so one moment. Let me do CLC to clear the, whoops, CLC to clear the command window. I'm going to put this matrix up. So now those vectors are pretty darn close to being the same, right? The column vector, the first column vector of the matrix A and the second column vector of the matrix A are pretty darn close to being the same. They're still linearly independent, but it's just like barely, right? And so if we do condition number on that matrix, look at what we got. Oh my gosh, what is that? What is that? We have 9.9999960, you know, 3869. Well, it's 9.9999960038690 E plus 07. What does that mean? What does that mean? At E plus 07 in the output. What's that stand for? What kind of notation would that mean? If you had to guess. Begins with an S, SCI. What kind of notation is that MATLAB's producing? Scientific notation. Good, Jonathan. Good, Mikhail. Good, David. So the number now, the condition number of A is basically 9.9999, you know, that number times 10 to the 7th power. And so what's happening is the condition number is rapidly increasing as the matrix becomes less and less invertible. And the matrix A is becoming less and less invertible because the column vectors of the matrix A are getting closer and closer to becoming linearly dependent. Okay, so that's something that I just wanted to bring to your attention because it'll be helpful for one of your homework problems. Are there any questions before I stop on this? Okay, let me go ahead and stop the recording on section 2.3. We've basically covered section 2.3 now, so I'll stop the recording.